Okay, so try this, guys. See if you can find this equation as both a sine and a cosine function on Unit 4, Lesson 5. I'll zoom in here for you. Okay, so this is what we have so far. The a value you should have found as a half by doing max minus min over 2. The c value you should have found as negative half. I would like you guys to focus on creating the cosine function to start here, and then I'm going to show you something with the d value of sine, because if we don't have a way of calculating either the d of cosine given the d of sine or vice versa, sometimes we have to estimate. So in this case, if I don't know what one or the other is, for instance on this location right here for the d value of sine, I'm not quite sure exactly what that is. So we're going to use the d value of cosine to help us find that d value of sine so that we don't have to estimate. Okay, so find the equation for cosine to start here.
For k, is it just 2 pi over pi?
What's the d value of cosine here? So we got the k value of 2. Does everybody know where that came from? We're all good? The period is from 0 to pi here. So that's how we get 2 pi over pi. How do I get the d value of cosine? What do we look for? The max. So where is the location of the closest max to the y-axis? It's at 0, yeah. So this is the d of cosine. So we actually have a 0 value for d. There's no phase shift here. I want to create the equation for cosine, and then I'm going to show you how we can find the d of sine using that equation. So we're just going to plug in our d of cosine to start, or all of our values into cosine. So I have half for a, 2 for k. Actually, I can just write this as 2x because our d value is 0. And then minus half for c. Okay, for sine, the d of sine, there's a little trick that I'm going to show you guys for the d of sine. So you can use this little trick if you're switching from a cosine equation to a sine equation, or if you have a sine equation and you want to make it a cosine equation. It's very similar to what we talked about again last year. But to switch between these two, I'm just going to make you guys, if you want, you can make like a little note here wherever you have some space. So if I'm switching from cosine to a sine function, and then vice versa, I'll tell you what we'll do for each of those. If I want to switch from cosine to a sine function, like what I want to do now, the sine shift, if we look at our graph here, the sine shift is further left than the maximum. Okay, this is always the case because the rising midline, of course, rises up into a maximum. So the rising midline is always going to be further left than the location of the maximum. Agreed? Okay, I'll say it one more time. The rising midline, this guy right here, that rises up into a maximum, will always be further left than the maximum. Agreed? Because that rises up into a maximum. So the d value shift for sine will be further left than the cosine d value. And what we need to know in order to figure this out is the connection between the regular sine and cosine graphs. So if we just slide back up to our basic sine and cosine graphs here, I want to take a look at these. Okay? Right now, we have the equation of a cosine function. So I want to look at this cosine function here. The cosine function, if I just extend this slightly back, just back to negative pi over 2. If I were looking for the location of the rising midline on a regular cosine graph, it is pi over 2 to the left, right? So here's my midline right here. That location of my rising midline is pi over 2 to the left. But I also need to consider any compressions or stretches that have happened to the horizontal of that equation. So if you guys remember from last year, we said it was like 90 over k left and 90 over k right. In this case, it's pi over 2 left and pi over 2 to the right. And I also need to consider that stretch or compression factor that could have happened horizontally. So this one is going to be further left, right? It's going to be pi over 2 to the left. Where am I here? A little further. So I will take any existing shift. So I'll take the d of cosine, and I am going to subtract pi over 2 over k. So when I think about pi over 2 all divided by k, or in other words, like from last year, this was like 90 over k. When I think about pi over 2 all over k, if I flip and multiply this, it will be pi over 2 times 1 over k, and I'll get pi over 2k, just as so that I don't have a fraction within a fraction there. So we said the d value of sine will be further left than what the d value of cosine is. So I will subtract pi over 2k. So take the existing shift of cosine, and then it's going to be pi over 2 to the left and also divided by k to account for the horizontal stretch and compression factor. Okay? The d of cosine, if I'm switching from a sine to a cosine function, I will take any existing shift of sine, so it will be d of sine, and it's going to be a difference of pi over 2k, but to the right. So if I look at the original graph of sine, I'll just sketch it for you guys quickly here so we don't have to scroll all the way back. The original graph of sine has a maximum at pi over 2. It has a maximum pi over 2 to the right. So I'm doing pi over 2 to the right and then also considering any stretch or compression factor that has happened. So that's how I can get from a sine to a cosine function if I don't know the d value of one or the other. I have to know at least one of them though in order to do that. Okay, so here I can find the d value of sine by taking my existing shift of cosine, which is actually 0. Okay, it will be d of cosine minus pi over 2k. d of cosine is 0 here. What's our k value?
It would be...
Oops, not equal. It's 2. So I'm going to do minus pi over 2 times 2, because our k value is 2 above here. And I will get negative pi over 4. Is negative pi over 4 a left shift or a right shift?
That would be...
Yeah, so it's like pi over 4 to the left. So when I put this into my equation here, I'll just do it right here. I will have everything exactly the same, except of course the sine will change to a cosine, and I'm going to change my phase shift. So this will be plus pi over 4.
Wait, where'd you get the other two? Sorry.
That's the k value. I'm plugging in the k value here. And then minus a half. Does it look like my shift, based on my graph here, does it look like my shift could be pi over 4 to the left? Does that look like it's accurate? This location right here? Could this be pi over 4 to the left? Yes, because this is negative pi over 3, and this is negative pi over 6. So negative pi over 4 falls directly in between those two, actually. So pi over 4 to the left does make sense for this location right here. Okay, I believe this guy right here is also on your summary sheet at the front of your unit package. Okay, so we're going to practice switching between sine and cosine one more time. Because for example 2, I'm going to create a sine and a cosine function for this. So does someone want to help us out? If we're looking at a sine function with amplitude 7, period of pi, phase shift of pi over 4 right, and vertical displacement of 3, what can we plug into our equation here? We'll call this guy g at x. Give me one thing out of A, K, D, and C. Sam? Okay, so A equals 7 because the amplitude is 7. Okay, what else? Alexandra?
K is pi.
Not quite. We can use K.
K is 1 over pi.
Not quite. So this is the period. How do I get the K value from the period?
2 pi over pi.
2 pi over period.
Yep, 2 pi
So it's
over
just
pi.
2.
So we get 2. Okay, what else? Someone give me another one here. X minus pi over 4, right? So this tells us about the D value. And last thing, vertical displacement of 3
That would be plus 3 at the end.
plus 3. Awesome. Okay, if I wanted to create a cosine function from this, I know that the D value of cosine will be further to the right from this pi over 4 here. If I wanted to figure out D of cosine, I would take D of sine and I would add pi over 2k. So it's a pi over 2 shift to the right plus any stretch or compression that has happened. So I would take negative pi, or no, sorry, it's positive because it's a right shift. So I'm going to make right shifts positive and left shifts negative if I'm putting these in here. So pi over 4 is a right shift plus pi over 2 times 2. That's the K value. So I'll get pi over 4 plus pi over 4, which gives me 2 pi over 4, or simplifies to pi over 2. Oops. So because I got a positive answer, is this telling me right or left?
Right.
It's telling me right. So if I were to write this sine function as a cosine function, we'll do 7 cos 2x minus pi over 2, because it's a right shift, plus 3.
Wait, how did you use the D of cosine steps?
So I'm plugging in the existing shift from sine, the D of sine, and then it's plus pi over 2 times the K value here. So the K value we found to be 2. And then I'm just adding these fractions and reducing. Does that make sense? Okay, so make sure you put right shifts as positives and left shifts as negatives in these equations. Okay, so those would be our 2 equations. Questions? Can I scroll? Oh, and answer is above for this one, sorry. Okay, the last little part of today is transformations of the parent functions. So when I introduced, or when we worked together to graph the sine and cosine functions, the wave functions, I talked about some important key points that we were going to use to do transformations of these functions. So this will work the same way we do all other transformations, but I want to make sure I know the key points of sine and the key points of cosine that I will transform to get my next graph. So here, the parent function here will be the sine function. So we'll start with the graph of the parent function, and then we're going to do some transformations. So we'll start with sine x, and we said the important points here are the points that are kind of on the outside of that unit circle, which were these guys. They're like the 90, 270, 180, 360 points, all those points from last year. Okay? If you know those 5 x coordinates, you don't have to memorize the y coordinates. You could actually just literally plug them into your calculator. So if I evaluate, making sure I'm in radian mode, if I evaluate sine of 0, I'll get 0. And then I'll just evaluate the rest of them in my calculator to get the y coordinates. Claire?
On the test, will you be like giving us like this stuff on the bottom?
Most of the time I will give you, like, it will be basically the same scale as this. So we'll get the points here by entering these into our calculator. These are my key points that I'm going to use for sine. Okay, when we go to do transformations here, leave yourself some space for the x coordinates. It's going to be 5 x coordinates. 1, 2, 3, 4, 5. Sorry, I just want to fix these. 3. Okay. So if I look, yeah, Alexandra?
Can you go back to
Example 3 is just this that we did above. Yeah. Okay, so if we look at our equation here of the sine graph, I have A, K, D, and C here. Can somebody set up the tops of my transformation equations here like we did in grade 11? How do I set up these equations that will help me transform my parent function points? Does anyone remember? Liam?
For x would be 1 over 2x plus pi over 3%.
Great. So reciprocal of the k value times x, and then switch the sign of the d value. So it'll be plus pi over 3. How about the y side? Liam?
3y plus 1.
3y plus 1. Awesome. Okay, so you do ay plus c. For this one, you do the reciprocal of k times x plus the d value, just as a reminder from last year. Okay, this is the same as how we did all transformations last year. It's not specific to trig. Yeah.
I don't remember the chart though.
Yeah, this chart is different. We just did a normal table last time.
Yeah, just because the only reason is because I need more space for the x's, because we're going to do, like, we need to find common denominators and stuff. Okay, let's start with the y's. I'm going to enter in each of these y coordinates. We'll multiply them by 3 and add 1 to get our new y coordinates. So 0 times 3 plus 1 is 1. I'm going to put that in for all the zeros here. There's no point in me calculating it multiple times. Positive 1 times 3 plus 1. That will give us 4 for that coordinate. And then for negative 1 times 3 plus 1, negative 2. Perfect. Those ones are relatively easy. For the x coordinates, they're not difficult. We just need to make sure that we find common denominators here. So we're going to start with entering in 0. 0 times a half plus pi over 3 will just give us pi over 3. And leave yourself a little bit of space here because I'm going to talk about after where we would actually place this pi over 3 here. Okay, let's just figure out the calculations for these first though. So I'm plugging in each of these x coordinates over here into our equation up here, and we're just going to calculate. Okay, so this will be pi over 4 plus pi over 3. Find yourself a common denominator there. So I think 12 is the common denominator, lowest common denominator. We will get 7 pi over 12. Okay, again, leave yourself some extra space below because we're going to do a few more calculations to figure out where we actually need to place that. Okay, plugging in pi. We get pi over 2 plus pi over 3. Again, find yourself a common denominator. I think that will be 6 for this one. And then add them together. And then 3 pi over 2. We'll get 3 pi over 4 plus pi over 3. Again, I think the common denominator here is 12 for each of these. So I'm going to multiply the left side by 3 on top and bottom. We'll get 9 pi over 12. And the right side by 4 on top and bottom. So when we add here, we'll get 13 pi over 12. Okay, and then last one, 2 pi. The 2 and 2 will cancel, and you're just going to be left with pi. And then again, common denominator. So 3 pi over 3 plus 1 pi over 3 gives us 4 pi over 3. Okay, this is nothing that you guys don't already know, other than maybe like we learned these new like radian points. But we're really just working with fractions here. We're creating common denominators. So if you know how to find a common denominator between two fractions and add it together, you should be good to go with this.
Wait, where'd you get 3 pi over 6 for 1?
3 pi over 6. So if I multiply this by 2, and this by, oh no, sorry, you're right.
Common denominators?
Yeah, but it should be 2 pi over 6. Sorry, it should be 3 pi over 6 and 2 pi over 6 here. I just put them in the wrong order. Okay, so that's all well and good. I found pi over 3 and 7 pi over 12 and 5 pi over 6. Where do I place these on my graph though? That's kind of the problem, right? It's like I don't really know where to place 13 pi over 12 on my graph. Like I have some labels up here, but it's a little bit harder to kind of understand exactly where those are in radians. But it's actually super easy to figure it out. All you're going to do is locate pi on your x-axis and decide on the number of ticks that is based on the given scale. So how many units do I need to go over on the x-axis to get to pi here with this particular scale? Okay, so pi here equals 6 units on the x-axis, agreed? Okay, 1, 2, 3, 4, 5, 6. With that information, I should be able to find the location of all the rest of these super easily. We're going to do just a really quick calculation. So if this is the key here, pi is 6 units on the x-axis here. If I switched the scale on you guys and I made pi equal to 4, just use 4 for pi, 4 units for pi. Okay, so here's how we're going to calculate it. If pi is 6 units, I'm going to plug in 6 units here, and we're going to divide that by 3, and we're going to get 2 units on the x-axis. Okay, pay attention here, guys, carefully, so that you guys get the idea. It's super easy once you get the hang of it.
Wait, what is pi equals 6 units?
So look up for 1 second. You see, on the x-axis, yep. Okay, so at 2 units on the x-axis, 1, 2, that's the location of pi over 3, and I am graphing the point at a y-coordinate of 1. Okay, so 2 units, again, 1, 2, it has a y-coordinate of 1. So that's where my point is. So this is pi over 3. Okay? For this guy, 7 pi over 12, I'm simply taking 7 pi over 12 and I'm doing 7 times 6 units divided by 12. What does that get me?
42 pi by 12, which
4?
I think 3.5.
I don't think so.
3.5.
3.5, yeah. So this will be 3.5 units on the x-axis, and I will graph the y-coordinate at 4. So let's look at 3.5. So 1, 2, 3.5 at a y-coordinate of 4. So 0.5, 3.5 up at 4. Okay, so I'm just graphing that. Any questions so far? Okay, so if you figure out how many units pi is, the scale could be anything. Doesn't even matter, like it doesn't have to be the same scale as this. We're just going to plug that in as the number of units of pi, and then we'll figure out the number of units for where we can graph the rest of these points. Okay, we're going to do the same thing with the rest of these quickly, and then we'll graph the points. So 5 pi over 6 is like 5 times 6 units divided by 6, and I think the 6's will just cancel there, and we're left with 5 units. Let's do 13 pi over 12. It'll be 13 times 6 units.
Wait, so you do 7 times 6 over 12?
Yep. So here it's going to be, what, 7.5, I think?
6.
Is it 6.5? That makes sense. 6.5 units. And you should start to see a pattern in your x's. What am I going up by with the number of units each time? It's 2 units, and then 3.5, and then 5, and then 6.5. What's the 1.5? So I could just continue that pattern if I wanted to, but if I want to just make sure that my calculations are correct here, we can continue doing that kind of idea. But I would predict that the next one will be 8 units, because 6.5 units plus 1.5 units should give us 8 units, which I think it does here. So 24 divided by 3, that's 8 units. Okay, so we're going to graph the rest of these points. 5 units, or 5 ticks over on the x-axis, up at a point 1. Okay, I'll scroll back down in a couple seconds. So 5 units at 1. 6.5 units at negative 2. So 6.5 at negative 2, that's right here, just after pi. And 8 units back up at 1 again. So 8 units is right here. Okay? This asks me to graph 2 cycles of the transformed function and 2 of the parent function. So if I wanted to continue this pattern, I'm going to continue the pattern with the y's, and I'm going to go 1.5 units for each of my x's here. So 1.5 units over should be up at 4 here, and then 1.5 over again down at 1, and 1.5 down at negative 2, and 1.5 back up at 1. So that's how I can extend my cycle pretty quickly here. So just repeat your cycle again, same number of units between your x's, and then we're just going to connect them all here. Okay, your function should not look like a zigzag. This is a nice, try to make your function actually curve here. Okay, and I would also like to graph our parent function here, so 2 cycles of the parent function. So just using these points down here, and we'll also extend it into the negative section. So I'm going to graph the points 0, 0, pi over 2, 1, pi 0, 3 over pi, or 3 pi over 2, negative 1, and 2 pi 0. And I'm also going to extend this back into the negative section as well so that I can extend my cycle. Remember, guys, that your cycles here should always go mountain, valley, mountain, valley. So when you're thinking about extending your cycle, past this mountain should go down into a valley.
Wait, were you
This is just the parent function here, so I'm graphing these points of sine x. Okay? And then we're just going to extend this back into the negative section. So extending your pattern over, it should go to negative pi over 2, negative 1, negative pi 0. So I'm literally just following what happened here to go backwards. And then 3 pi over 2 up to 1 and 2 pi 0. And that's the graph of our parent function. We'll call that y equals sine x. Okay, so I know if I extended my graph correctly, if I'm going mountain, valley, mountain, valley. A lot of times I see people extend their graph and they kind of like do it as a vertical, like a horizontal reflection, like symmetry like this. If you're going mountain, mountain, there's a problem with that. It's always mountain into valley, nice smooth curve, okay? Are there questions on this that I can clarify? It's pretty similar to last year. The only extra thing is figuring out where to place these radian values on your graph. Okay, can I go to the last one here? I'll take that as a yes.
Wait, sorry, what did you do?
Can I go to the last question here? Is that okay? I do. I really want to. Okay, so for this one, I want to graph this function for cosine. We're going to start with the key points of the cosine function. So this will be y equals cos x. Same x coordinates, so 0, pi over 2, pi, 3 pi over 2, and 2 pi. Again, you do not have to memorize the points. If you know these 5 values, you can enter them right into your calculator, as long as you're in radian mode. So this will be 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, and 2 pi, positive 1. Again, I'm going to leave a little bit of space for our x coordinates here so that we can calculate those like number of units, that kind of idea. Can someone help us set up our equations on the top of this function here? Given our equation above. So this is A, K, D, and C. Jonathan.
It would be, so 2x minus pi over 4.
Great.
And half of y minus 2.
Awesome. Okay, so reciprocal of the k value is a half, so I'm using 2 times x, and switch the sign of the d value. It looks like plus pi over 4 in the equation. I use minus pi over 4. And then the a and the c should look exactly as they look in the equation. Okay, so it's just ay plus c. All right, we'll do the y values really quickly here because they're a little bit simpler calculations. So 1 times a half minus 2, that gives us negative 1.5. I'm going to put that in for both of the y coordinates that are 1. And then 0 times a half minus 2, that just gives us negative 2 for both of the zeros here. And negative 1 times a half is negative half minus 2 is negative 2.5. Okay, now each of your x coordinates needs to be plugged in here. So 2 times x minus pi over 4, that just gives us negative pi over 4. If you would like, you can calculate the number of units quickly as we go here as well. Always double check, pi is not always going to be 6 units. So we need to count on the x-axis, 1, 2, 3, 4, 5, 6. So in this case, pi is 6 units. And because of that, we can use that idea to calculate our units for these things here. So negative 6 units divided by 4. So what do we get for number of units here? Okay, so that means 1.5 units left, right? Okay, we'll keep going with our calculations. 2 times pi over 2 minus pi over 4. We'll get,
Negative 6 units.
so remember we take a look at where pi is, how many units pi is, and then I'm subbing in that as the number of units for pi here. Just so we can figure out where negative pi over 4 is on our graph. Okay, so pi minus pi over 4, you're going to find a common denominator. That's 4 pi over 4 minus pi over 4. And that gives us 3 pi over 4. And then, again, you can sub this in and calculate. Yeah, Liam? You sure? So we'll do 3 times 6 units divided by 4. And that will give us where to place this point. 4.5, thank you. Okay, let's keep plugging in here. 2 times pi minus pi over 4. And then we'll need to find a common denominator. So I think that will be 8 pi over 4 minus positive pi over minus 1 pi over 4. That gives us 7 pi over 4. So 7 times 6 units over 4. What do we get here? Trying to crack your knuckles louder than me. 10.5. Okay, so what are the number of units that we're going by each time? How many units in between each x-coordinate? 6. Okay, so I'm going to really quickly find the last 2 here, and then we won't have time to graph today. We'll finish the graph tomorrow, but
You're joking.
so this one gives us 11 pi over 4. That should be, if I add 6 units to that, this should be 16.5 units. The next one will be 22.5 units, just adding 6. And 2 times 2 pi minus pi over 4, that should give us 4 pi minus pi over 4. And that needs a common denominator, so we'll get 15 pi over 4 for this one. Okay, if you want to try graphing this one, it's a little bit more challenging because you're only going to be able to fit one cycle on here, so you have to actually extend into the negative section. But we will finish this guy tomorrow. I do want you guys to finish up Unit 4, Lesson 4, and try a couple questions for the transformation stuff. Let's just stop this here.